let us start. We have actually two talks in this session. The first one by Rose Cersonsky from Wisconsin. So I'm looking forward. I will wave my hands and looking forward to. She's combining apparently talks from her first ever work and her last work. So
most recent. I've got many more to come. Hi everyone, I'm Rosie, and as you were saying, it's going to feel a little bit sarcastic today because I'm talking about literally the first paper I wrote as a graduate student and my most recent paper, because my initial work was in packing in my graduate research, but the paper I'm going to talk about at the end is a little bit to stoke some conversation because it is not about granular matter. It's about molecular systems where we have a lot of really competing forces and it's really difficult to understand them. So to start, the first question I'm going to address is what is the role of packing in the self-organization of particles? So kind of a through line through a lot of my work has been understanding and decoupling the very complex competing forces in self-organization. And for reference, even though I'm the child of a mathematician, I am not a mathematician myself. I am a molecular scientist and a computer scientist, so you'll see that kind of trickle throughout here. So this is a video I actually think I did steal from Michael, where when I'm talking about self-organization, I'm talking about particles that are creating order with no external forces. Essentially, they are just using volume exclusion to create some sort of ordered system. When we see this in both oblate and prolate ellipsoids, that if you just throw these things in a box, simulate them with the NBT ensemble, over time, they're going to create some order. So what role does packing have here? And in order to get to this, I have to define packing, which is a very terrifying thing to do in the second talk in an entire workshop about packing. But here we have to for the sake of science. So I'm going to say that packing is what particles will do based upon free volume exclusion at infinite pressure. So what role does that have in the self-assembly process? And from this, we can take putative packing surfaces. So this is a putative packing surface saying, what is the crystallographic pattern that emerges under infinite pressure in these systems? And we're not talking about under infinite pressure regarding kinetics. We're saying, like, let's ignore kinetics and just say it can get to the thermodynamically optimal state. So this specific one is for a family of shapes here. So we see here we have a cube that goes all the way down to a rhombic dodecahedron, to a truncated cube, and an octahedron. And so this family of shapes will be very important in what I'm about to go through. Specifically because when we started this project, we wanted to think, if packing influences any self-assembly processes, which would they affect? And so we said, okay, the most likely place to find the influence of packing and self-organization is hard particles. Specifically, hard particles that we know pack and self-assemble the same structure. And there are many different hard particles that pack and self-assemble different structures, but specifically, we know we wouldn't find much influence there. Let's look at the ones where it does. So if we take this shape family, and I'm going to turn it because I have a better convention that I like to think about this one. So here is how I think about this shape family. There are three different shape structure pairings in this shape family that both pack and assemble the same thing. So rhombic dodecahedra both self-assemble into the face-centered cubic lattice and pack into it. Cubes, which I hope this is not a surprise to people in this room, they self-assemble and pack into the cubic structure. And then truncated octahedra both self-assemble and pack into the body-centered cubic structure. So in order to understand this, we actually need to create a thermodynamic ansatz. So when I was talking about these hard particle volume exclusion simulations, specifically, I am simulating them with this thermodynamic canonical ensemble, where our free energy is dependent on our internal energy and our temperature and our entropy. But because we're saying hard particles, we're going to say that if they're overlapping, their internal energy is infinite, and if not, it's zero. So we just ignore this term for now. But what some of my colleagues did is they actually extended this, thinking about, okay, well, what if we're working in a system where we have varying shape? Well, we can think about this mu, our alchemical potential, and this alpha, our alchemical variable. where going back to the shape family from before, our alpha is actually going to be the truncation parameter from one axis to another. So here we have this extended ensemble where we have defined essentially a thermodynamic representation of shape. Now, using this extended ensemble, we can actually define one Maxwell relation. And so I am the malaprop of the world, where if I say Maxwell equation, I'm very sorry, I've done work in electromagnetism. And so I will constantly throw one in for the other. But here what we have is a Maxwell relation that actually lets us look for the signature of packing in our self-assembly systems. So here I've changed it. So it's in terms of our volume density phi instead of volume, but it's a trivial transformation. So what does this say? This says that the thermodynamics of our system is consistent with packing when the derivative of our alchemical potential, so our response conjugate variable to our chemical shape, with respect to pressure, equals that of our packing surface with respect to shape. So now we can take that putative packing surface from before, zero in on a section. So if I zero in the section having to do with FCC and rhombic dodecahedra, and look at the local derivative, we can actually look at when this system is assembling or behaving based upon how it would in the infinite pressure limit. So that's exactly what we did. So I computed the alchemical potential. There is a whole lot of mathematics in the end of this paper. I am not going to get into it today because, as you will find, it has been 7 years since I went through this. And anybody here willing to do the mathematics I did 7 years ago on a board in front of a bunch of mathematicians? Not me.
What about a bunch of engineers?
You can write whatever you want.
Yeah, it's one method.
I think I will need. I think I will need a third cup of coffee before that one.
Okay.
I don't want to have flashbacks to my defense in this moment, but
You know,
Can I ask you an easy one? I think I just fit the packing surface. You have a picture of it. But
Yeah.
I missed what you meant by that.
so that is so the way that it's plotted is it's the highest volume density
Okay.
at which a single shape can go. But the way that it's constructed is by looking at the intersections of different structures.
Your two parameters, alpha 3 and 4, are the domain of your picture.
Yeah, so it's our vertex truncation.
Got it. Thank you.
can I ask you a question?
Of course,
To calculate this derivative, you need F, right?
yes. Well, not exactly. You can use the acceptance ratios of it within the shape space. So essentially trial, do I want to move to that shape or not?
Okay.
And use the Benedict acceptance.
So you don't need an entropy?
Well, so essentially by querying the acceptance ratios and getting those probabilities, you get a proxy to entropy.
Okay.
Yeah, so there's a lot that goes into essentially just how many calculations I did here.
Yeah, right.
But
Part of your defense question, I bet, yeah. So you managed to avoid directly calculating an entropy function for this crazy space. Right?
correct,
Okay.
correct,
Good.
directly.
Yeah, good.
But we all know entropies and probabilities,
It's in there, yeah.
they're cousins.
Yeah.
So, yeah, so this is what we computed. So here we have the alchemical potential with respect to our pressure. And what you can see, this dotted line really just denotes, okay, at around 80% volume fraction, we're seeing a signature of packing. Here's the twist though. Self-assembly occurs down here at around 50–55%. And even if we were going to say, okay, what is the highest density at which we still have spontaneous disorder, where we have order formation, that's a random close packing here, that is still significantly lower than our packing onset. And this occurs for our others as well. So here we see truncated octahedra in our body-centered cubic system, and even more egregiously, cubes in our cubic system do not pack until 95% volume. So what we really rationalized here is, okay, packing is not the driving force to self-assembly. So the way, again, we've defined packing is what particles will do under the limit of infinite pressure. And really what this comes down to is rotational entropy has a role in self-assembly, a very important stabilizing role. So now I'm going to take a massive left turn to understand other complex interactions. Yes,
Can I interrupt you?
of course.
So you allow your particles to rotate magically through each other and
Not through each other. It's still hard particle exclusion. So they're rattling next to each other.
they agitate, keep going until they
And
can.
that's the temperature.
And they get pressure that as they can't agitate anymore, as they pack more.
So the ones that we're doing, the ones that I showed in the original were NPT. The second one, we were talking about NPT, because that's where we need to compute the alchemical potential. So when they're rotating, essentially, these are hard Monte Carlo simulations. And so that means that you're querying different rotational and translational trial moves, where you're saying, can I move, a slight bit over? Can I rotate a slight bit over? So you're exploring all these different microstates. And so there is rotational entropy in these systems whenever you are able to have a large number of microstates just based upon that rotational degeneracy. Yes.
Yeah, just to understand, I mean, you say that, packing is not the driving force, and I mean, it depends on the decision, but then you say, okay, the rotational entropy is important, the entropy is the empty volume, so it's packing.
But so if you went with just the volume exclusion argument, then you are going to go with the things that maximize the translational entropy with disregard to the rotational entropy. The free volume exclusion really just
Because you take off the joint exclusion, it's not enough.
the free volume
But the
exclusion
free
is
volume is the one that gives you the rotational entropy.
so.
That's my argument.
Well, no. So free volume arguments and rationalizations of crystallization are that you're going to get full face-to-face alignment, which is a translational entropy maximizing postulate there, versus the rotational entropy is lessened when you go full face-to-face. Did you have a question, Philip?
Yeah, so in that regard, if you say the rotational degrees of freedom become more and more important, this means that everything tends towards what hard spheres would do in self-assembly.
Yeah, there's a really great unpublished chapter in my thesis if you ever want to think about it. Because as a lot of people know that this extended thermodynamic ansatz from the Glasser group was used for digital alchemy. How do we figure out what shape best thermodynamically optimizes a system? And I was making an argument with Sharon for years, that given the way that it's set, we're always going to be fighting against the spherical FCC well, because that's what optimizes rotational entropy. And I showed her a bunch of things of like, how can we figure out that there is this ground state of shape space that is FCC and spheres? And yeah, no, there's a bunch of unpublished work, literally, hit me up. That also shows that there is a shape phase transition in FCC when you go from the rotational entropy maximizing shape to one that is more attuned towards the FCC structure. So yes, there is always that battle, and it is one of the things that I think will hinder certain structures from actually forming, because digital alchemy just ensures that something is thermodynamically stable in a structure, not that it will form it. And so there's a lot of different arguments to be made about kinetics of pathway. Literally, I can send you the PDF. There's like 150 pages of advanced structures though, so like ignore that. Yeah, so there's a lot still to be said about these ensembles themselves. But now I'm going to take a huge left turn. Permission to do so? I'll be here all week, so y'all can hit me up. Okay, so I'm going to give you a little bit of context here. What I've just talked about was all from 2016 at the University of Michigan. What I'm about to talk about is from 2022 at EPFL, where I was doing a postdoc in computational chemistry, where the molecules matter. And so here I was looking at a different problem. Given a set of molecular chemistries, what forces are most responsible for binding the crystals together in solid form? So this is a really big problem in the pharmaceutical and drug stabilization area, because essentially what you have are all of these different molecular entities, and you're trying to figure out what polymorphs are going to occur, especially in co-crystal systems. And in order to do this, people typically use synthon and tecton hierarchies to predict what's going to happen. So to give a little bit of understanding, so molecular packings, and this is why I thought it might be appropriate to talk about, are often rationalized by supramolecular synthons, libraries of intermolecular interactions between different moieties. And then tectons are the backbones on which we build these synthons. Now, experimentally, typically, and I'm still saying up until the last couple of years, the ways that you figure out these hierarchies is you take molecules that have multiple different functional groups, you mix them up under crystallization conditions, and then you figure out what shows up the most. Quite literally an arduous process where you say, okay, I see this one in 70%, I see this one in 30%, therefore, this is a stronger synthon. Computationally, what people would do is they would go on the crystallographic structure database and say, of all of these ones that people have seen, what synthons do I see most often? So this wasn't really satisfactory to me because it's very ad hoc and it's very dependent on what data set you have. It's very dependent on what you're actually trying to understand here. And it might change very much based upon conditions of crystallization. So I'll say computing the relative energetics of these interactions is very difficult though. And you'll see a lot of different papers talking about how we need this level of quantum theory or this level of quantum theory to justify macromolecular crystallization. And that's because you have a lot of different stable polymorphic forms that are very close together in energy. And so therefore, just using this functional versus another might change the ranking entirely. And kind of the classic example of this is in the late 90s, ritonavir had to be pulled off the market because a bunch of computational chemists said, okay, we figured out the stable form of this system. And then actually what happened when they synthesized it is a less water soluble polymorph emerged that was a more stable form. And this literally cost AbbVie, I think like $250 million. And so this is why I write in all of my grants when I say like, just give me 200 grand. So what we were doing here is we were trying to leverage atom-centered approaches in machine learning to be able to attribute different sorts of energetics to different sorts of functional groups. So to start, and this is the reason why I'm kind of going into this other side, all machine learning models require that we translate our physical system into some sort of input space for the model to operate on. And there's a lot of theory that goes into what is this input space, what is the model, what are the data of all of these things. But the way I think about it is say I've got a molecule right here, a nice ethanol molecule. Well, I can choose to represent it in text form. I can choose to represent it with a smile string, which is a simplified text form. I can choose to represent it numerically. And these different representation choices influence how much data you'll need, what sorts of models you can run, what sorts of properties you can learn. So I typically think about thermodynamic contexts, which are quite complex and quite expansive, where we're trying to map some sort of structure space into some sort of feature space. And specifically for this problem, I wanted to think about additivity, where my molecule is a sum of its parts. But I also want to think about something that's smooth with respect to my molecular chemistry, something that's complete, and something that abides by the symmetries we know to be true about the physics. There are many different options. If you are interested in the different theories and the different ideas, this is a really great 50-page review here, written by an old colleague of mine. But there's a lot of thoughts that go into, okay, how do we represent these things? So I'm going to use specifically a formalism known as the smooth overlap of atomic positions. And what this does is it assumes all of my atoms are Gaussian. And this is based upon the early theory on the nearsightedness of atoms and how their effect goes out. But specifically, I'm going to think about neighborhoods. So if I sit on an atom and I look out, what do I see? Well, I can represent this as a histogram. Here we have a histogram essentially over spherical harmonics and radial bases of our 3-body correlations. I don't have time to get into this today, but I'm more than happy to get into it on Friday, as well as any time that I'm here. But essentially what we get is for each atom a signature of its environment. And then the most naive way, there's also a lot of theory about how we combine all of these signatures to represent a whole molecular entity, is to just take the average. Now, I'm going to go, unfortunately, a little bit fast because I've been soliloquying a little bit too much up here and I'm running out of time. But essentially what we've shown is if you take these molecular crystals, and we're trying to specifically learn the lattice energy, the binding energy between the molecules, it's not sufficient to take just the signature of our crystalline environments. From that, we get an okay regression. I'm going to show R² values up here, but I have all of the RMSEs and MAEs elsewhere if anybody wants to see. And to kind of benchmark it, if we were just use the gas phase environment, so the environments of the atoms knowing absolutely nothing about how they're interacting, it's not that much better to just take the crystalline environments. But the key here is, what if we take the difference? Because that's actually what we're trying to represent. The energy gained by these molecules in the crystalline environment. And there we see our final jump in energetics. So this is just a linear model on these descriptors. I love using linear models on 3,000 data points, which in the machine learning community is what we call a tiny data set. So then, using this remnant fingerprint, we determine our weights to get our binding energy. And we can take weights for any single atom because we used an additive descriptor or a collection of atoms. So this is our carbonyl group in acetamide, and we can figure out the relative energetics of that carbonyl group in acetamide. So I did this for about 70,000 molecular motifs in our 3,000, where essentially what we can do is take SMILE strings and SMART strings to automate identification of different functional groups. So for here, we can take our carbonyl group, our methyl group, and our primary amine, and figure out exactly what the energetics of these different groups are, using some convolution to be able to make sure that we're not over attributing to every single atom. But this reflects what we see in our crystal. Where are things interacting? So I'm unfortunately, because again, this is my first time giving this talk, and I apparently planned a 40-minute talk here. Gonna have to stop here, but I'll just leave you on the note that we were able to do this for all these different moieties over a large expansive data set, and that we were able to use simple mapping techniques in order to understand and analyze these systems of being able to say, why do these different functional groups land in the same space as others? What makes a good environment for this functional group? And everything, I'm going to do a real quick to the end. Everything is here, including the open data. But I'm going to take one more glut in a second.
Sure.
Because as you might have noticed in our field and others, we are still nowhere near gender parity. And I like to take a moment at the end of my talks to talk about this. Because why? Especially in the field of mathematics, computer science, and theory-driven systems, we are actually going down in recent years, which does not match what we see in terms of the promoting and marketing in the field. So I actually work together with a chemist at Warwick in Coventry, and a physicist in Wellesley to figure out what is the data showing us, because we all can have anecdotes about why gender equity is far off, or gender equity, oh, we're already there, why are people still complaining? But the data shows that especially women and people of color are still being undercited, underfunded, underpromoted, everything across the board. And so we put together this whole, I would say, treatise on gender equity that I would encourage everybody to check out, because we put a lot of time and effort making sure it reflected the way that we want to move forward as a community. And with that, I will take any questions and say that I'm hiring, so please hit me up.
Definitely something for discussion. If you want to-
I have lots of thoughts.
Yes.
Lovely talks. I've got a question for each of your parts. Let's start with the back one. The weights. Can you put some experimental conditions into those weights? Or how can you reflect different conditions under which you form your crystal? Is it in the weights, or how do you put it?
So it would have, so that's going to be also in the energetics that we determine. So here we're working just with ambient condition energetics, which we use as a proxy to just figure out potential energies. So we can then put in, there's still a lot of discussion of how we actually include the temperature dependence and the solvent conditions into this process. And that's an great open question. But these are just configurational descriptors. So we could weight them by, okay, in the solvent, they explore this sort of geometric configurations, but
So you do this as a nice interdisciplinary work where an experimentalist does this under different conditions to do your machine learning and learn how things change.
oh, absolutely.
I can see a very good point there. The first part, the math question comes here. So if you have a polyhedron, you ask what's the best packing you can do. So naively you would think, what kind of lattice can I find? What are the latest properties? So something we've been doing from a different end is to think, say, about the icosahedron and polyhedron line, and then ask, how actually can I align different copies of it with the symmetries that the unit has and the lattice has to optimize its packing? Is this related somehow? So is there a lattice question lurking in the background?
Yeah, so I would actually encourage you, so I will make these slides available. The FISREV X that did all the putative packing surfaces, they were doing lattice arguments. And yes, although the person next to you might even have more information on that one. So that was thinking about how we have the symmetries of these different systems.
Cool, yeah, thanks.
If you write the paper, you need to know.
They want to
Yes.
I'm glad Ryden got to ask the first question. Fantastic talk. I wish you had 40 minutes, but I'll stick around.
Come back Friday, I got a block.
I'll be around. Since you brought this other topic up, I wonder if you have thoughts on at what age the intervention to get more people interested in math and science, but whatever they look like and everything. Because I've often thought myself that you better start about age 1 or 2.
So there's two really big problems right now. So there is the recruitment problem that I think that the correct age is 6th grade. And I'm talking American style ages because that's what I know. Because you actually see an inflection point in women's performance in math at around that age. They're outperforming men earlier than that age, and then you have an inflection point. But a huge problem right now is the retention problem. We lose women in the field at a much higher rate than we lose men. And so that is shown across academia. Women leave in associate and full professor rank at a much, much higher rate. And that propagates into how we recruit people, because one of the biggest things that we can do to recruit people is making sure that there are role models that reflect them across all different ranks. And so if we're losing women in positions of power, and then the young people only see people that don't represent them in positions of power, they get discouraged. And so those two things have to go really, really hand in hand of how we make our space more equitable at every single rank, so that people can succeed that weren't traditionally meant to succeed in this space at every single rank.
While we are taking more questions, maybe the next speaker could start, and we have this, and you can answer maybe one more question.
Feel free to take a picture, but I will share.
Okay. Any more questions? Last burning questions while we are changing speakers? Okay, thanks so much, Rose. That was fantastic.